This is fundamental problem 14 from chapter 17. The 100 kilogram cylinder rolls without slipping on the horizontal plane. Determine the acceleration of its mass center and the angular acceleration. If it rolls without slipping, that means you must have friction, because if you did not have friction, the cylinder would be sliding on the surface and not rolling. And because it's rolling without slipping, that means it's static friction. So if it's not slipping on the surface, you have static friction, and that would be acting this way. I don't know what that force of static friction is. So for this problem, I can use Newton's second law. I can look in the x direction. I can look in the y direction. The cylinder is not accelerating in the y direction, so the sum of the forces in the y direction is equal to 0. So the y component of the acceleration of the mass center is equal to 0. You could use this equation if you wanted to find what the normal force was. It would just tell you that the normal force is equal to the force of gravity. When you sum up the forces in the x direction, this is equal to the mass times the x component of the acceleration of the mass center. If I was going to use this equation, I know this 200 Newton force, but I don't know what the force of static friction is, and so I would have two unknowns in this equation. So before we take a look at that, let's look at the sum of the moments. Now, when I sum up the moments, if I sum up the moments about this point here, then the force of friction will not appear in my equation, and this is good because I don't know what the force of friction is. And this is the instantaneous center of zero velocity. And so using equation 17-19, we have the sum of the moments about the instantaneous center is equal to the moment of inertia about the instantaneous center times the angular acceleration. Okay, so we need to know the moment of inertia about the instantaneous center for a cylinder. Now, if you go to the back of the book, they don't give you the moment of inertia about, that would be an axis like this for the cylinder. If instead it was a thin disk, the moment of inertia is 3/2 mr squared about the z prime axis. The moment of inertia for the thin disk about the z-axis is the same as the moment of inertia for the cylinder about the z-axis, and that's 1/2 mr squared. And since they didn't give us the moment of inertia that we want here, we could use the parallel axis theorem for the cylinder. The parallel axis theorem says the moment of inertia for an axis going through the mass center plus, where's my equation sheet, plus the mass times d squared, where d is the distance between the original axis, which was z, and the new axis, which is here. That distance, though, is just the radius. So that gives me 3/2 mr squared. That's the same thing that we have here for the thin circular disk. So you could either use the parallel axis theorem, or that recognize that if you're using the z-axis or the z prime axis, the height of the cylinder doesn't matter, so you could treat it as a disk, and you get the same thing when you're looking at the z-axis and the z prime axis that we have for the cylinder here. Okay, so now that I have that moment of inertia, I can say this is 3/2 times the mass is 100 kilograms, and the radius they give me here is 0.3. So that's 0.3 squared times the angular acceleration, and the moment of inertia is 13.5. So that's 13.5 times the angular acceleration. When I sum up the moments about the instantaneous center, I use the distance between the instantaneous center and where the force P is being applied. And if I draw a vector, I just want the perpendicular component of that vector. So that is the radius, which is 0.3. So for the moment, that's 0.3 times 200. And I can solve now for the angular acceleration, and I get 4.44 radians per second squared. Okay, now if I wanted to, let's see, I guess that doesn't really help me to use this equation here because I still don't know the force of friction. So if I'm looking for the acceleration of the mass center, I'm going to have to find that using what I have here. Once I find the acceleration of the mass center, though, if I want to go back and find the force of friction, I could do that using the equation that we have here. Okay, and remember, well, they didn't give you a coefficient of friction, but if it's static friction, then finding the normal force doesn't help you to find the force of static friction unless you happen to know it's at its maximum value. Okay, so what we have to do here to find the x component of the acceleration of the mass center is to recognize that if the cylinder is rolling without slipping, then the acceleration is equal to the radius times the angular acceleration. The radius is 3, the angular acceleration is 4.44, so that gives me 1.33 meters per second squared, and the y component of that vector is 0, so you can just say that's 1.33 meters per second squared in the I-hat direction, or you can just say it's going to the left. So that concludes fundamental problem 14.